Okay, off we go. Welcome back, everyone. I hope y'all had a nice fall break, R&R, and all that. And just a reminder, getting back into the swing of things, don't forget about the attendance quiz, attendance code. Again, here's the code. The clock's ticking. You probably have about a minute and a half left at this point. Make sure to get that in. And here's where we were last time. We were talking about this new idea called a triple integral. The main thing to realize about a triple integral is it's a shameless ripoff of the idea of a double integral. The most important idea of which is that it is a shameless ripoff of a single variable integral, right? In all three of these cases, what we're talking about is having some sort of a domain, whatever it might happen to be for whatever reason, on which we are interested in some quantity. Who knows what that quantity could be? It's very important that we not pigeonhole ourselves, right? Any sort of a quantity with the one asterisk, it does have to be an accumulating quantity. This is my term I like for a quantity where the whole is the sum of the parts, right? So mass, for example, is a nice, physically relatable example of something where the whole is the sum of the parts. That's how mass works, right? So any such quantity, well, you can take your domain, chop it up into little pieces, and then add up what you get on each little piece. And that's the sort of the summation element of the triple integral construction. Why don't I go full screen? Then what do we do on each individual little piece? Well, on each individual piece, we need this to be the case. We need to know that what we're interested in on that little sub-box, whatever that quantity is for that box, we need it to be something times size. Not length, not area, now volume, right? Now, I like to refer to this something, the integrand, I like to think of this as being a density. After all, if you think about it, if this is a stuff of some sort, the thing you multiply by size to get stuff is stuff per unit size. That's kind of what a density is. All right. Okay, so basically the same strategy for computation that it underlies the idea of a double integral and a regular single variable integral. So we're going to use analogous notation, analogous terminology, etc. Beware, reminders. This is just a real quick sort of summary, getting this back up to where we had been. Beware of your intuitions and how you think about this and how you visualize this construction. Right, there is a kind of a dead end point of view there that is really nice for single variable, and therefore tempting to kind of continue on. And reminder, I'm kind of pushing this point of view right here. I encourage you to try to think of integrals as accumulations of stuff over domains, and kind of try to, I don't want to say forget, because that's not true. These can be useful as well sometimes, but try not to be so attached to the idea of thinking of it in terms of graphs, because again, losing deal for triple integrals, right? It's not possible. Okay. Alrighty. Again, we kind of run out of dimensions for making certain kinds of arguments, so I can't justify this, but I can assert, I imagine you'll probably believe me, that triple integrals can be computed with iterated integrals. And there's we would expect there to be a sort of a geometric version of this, but again, it gets four-dimensional, and it's not reasonable, right? There is, of course, also an algebraic way to see this. I don't think it's appropriate to the course. But it's, I think, pretty plausible. So hopefully that's at least somewhat satisfying. And of course, on our diagram, what that represents is this right here. That when you write something as a triple integral, you can rewrite it as an iterated integral. And this is sort of the middle step in our three-step process. In some sense, the whole point of Riemann sums is that they are made to connect to applications. Right? And then what's the point of iterated integrals? Well, they are highly computable with the fundamental theorem. You start in the inside and integrate your way out. Right? So we have this three-step process where step one, write the answer to your question as a triple integral. Step 2, rewrite as an iterated integral. Step 3, plug and chug. Okay. All right, and I think this is about where we were. Yeah, we worked out an example. Oh, excuse me. We did also talk through this. Let's hit the broad strokes on this again. So how do we find our bounds in the case of non-rectangular domains? And I'm going to say it's analogous. It's morally equivalent to the process we did for double integrals, right? And that is, you start on the outside, and we argue, for example, that, well, look, x starts with this back point, the farthest back point there. That gives you your lower bound x1. And then it ends at, well, this kind of front point here. That gives you your upper bound for x. And just like with double integrals, once you found your range of values, you fix a value. We're going to fix a value of x. Now we focus our attention on that x slice. So here we're going to look at this one cross section. This is an arbitrary cross section of our solid. That means we're going to think of it as being fixed, but it could be any. At different times, it will be all of these different values between x1 and x2. So it could be any slice, but we're going to think of them sort of one at a time. And then on that slice, you move to the inside, you think about your next variable, and you slice again, and you keep thinking about ranges of values and slicing again, etc. And the punchline is you end up with, well, here, okay, let me walk through the next step here. So the next step, we look at the range of values of y, our y slices on our x slice look like that, and we can talk about first and last. And then when I fix both x and y, now both x and y fixed, we're really talking about a point in the xy plane that's now fixed. And then above that, we need to ask, where does z start and where does z end? Okay. So pretty much the same slicing process that we had for double integrals. It's just, okay, now it's three-dimensional. Now there's 3 steps in the process instead of 2. Other than that, it's pretty much the same. Okay. All right, do keep in mind, I think this is worth reminding you of, and I'll say this for the new inside-most integral because it's kind of the new one in some sense. Don't forget where this comes from. This inside integral represents trying to think about what's happening in the z direction with the assumption that x and y have been pre-chosen. In other words, that x and y are to be thought of as being constants. And you can look at this integral in the z direction. As we go in the z direction there, we are literally not changing x and y at all. So I'm going to say we treat x and y as constants because they literally are behaving as constants while I work on this dz integral, right? As I do that integral, x and y literally don't change. Everybody happy? Okay. Let's do one. Let's get our hands dirty, do an actual example. This first example I want to do is I'm going to say kind of an easy one in a sense. It's easy in the sense that the algebra involved is not going to be getting in our way, right? There's no tricky algebra there. Also, the geometry is not going to be particularly challenging. We look at this tetrahedron, but all 4 of those planes are pretty easy to draw. I think it's pretty easy to see what our shape is. Even though the geometry is pretty straightforward, we're going to find that there's a certain amount of geometric challenge in this because we're going to have to visualize slicing this up and things like that. So we're going to rely heavily on our picture, and you're going to hear me make the following case several times. Make sure you draw yourself a good picture. We're going to need our picture. We're going to appreciate having our picture as we go along through this process. Okay. All right. Is everybody with me so far? Everybody ready to dive into this details? Okay, off we go. No particular reason I'm going to do the slicing in this order. We do have 6 options. We could do any of them. In this example, kind of doesn't matter that much, so they're all going to look pretty much the same. But arbitrarily, let's do it in this order. You got to pick something. So let's think about our x bounds. There's the x-axis. That represents a constant value of that variable x. That's what we mean by an x slice. And the x slice, geometric appeal, the x slice looks about like that. Okay, so as usual, we just got to think about first and last. Where's the first x slice? Where's the last x slice? And what are those coordinates? Well, the first x slice, I think, is pretty straightforward. There it is. I mean, it's in the YZ plane. It's in the plane whose equation is x equals 0. What do I know about x when I'm in the plane x equals 0? And the answer is I know it's 0, right? So again, sometimes you get freebies when these freebies reveal themselves. Take them. All right, what about the last value of x? Well, this one's a little bit non-trivial. Now, I think you could probably look at this picture and just kind of see it, what the value of x is for that last x slice. But let's talk about the process. What can I say about that point? And here's where the picture is going to start to get really useful. Here's where we really need the picture. Well, I know, I can see it from the picture, that the point I'm interested in is part of that face. Thank you, picture. Got to have that from the picture. Right? By the way, that face, of course, the equation is given. Whoops, wrong one. Sorry, it's the equation's given. It's that right there. So that's the first thing I know about this green point I'm interested in. What else do I know? Well, I can see it's in this face. Again, the equation is given. And so I know that about this green point. And again, got to look at the picture. From the picture, I can see that that green point is in this face. And again, that face, the equation is given, and so I know that. So keeping in mind, what I'm trying to find is I'm trying to find what is my upper bound for x. This is the point that is that last x slice. I know it's got to be on all 3 of these planes, therefore it has to satisfy all 3 of these equations. Recalling, just to be careful, I am looking for x. I'm therefore going to solve in this equation for x. And I get 1. What do you think? Everybody see the process? Notice the pattern, very familiar from what we did back with double integrals. You identify, for any given bound, you identify the relevant point. The point is on certain shapes. They're not curves anymore, right? Now they're surfaces. Those surfaces have certain equations. Solve for what you need. There's your pattern. Okay, moving along. So we now fix a value of x, so we're going to focus our attention on this x slice. We now ask the natural next question, which is what's the range of values for y? Okay, well, let's see here. Y slicing goes that way. That means, oh gosh, perpendicular to that axis is like this. Can you think about how do those, what do you get when you slice like so? You slice our existing slice. And of course you're going to get sort of line segments that go like about like this. So there's our Y slicing. Is that cool? Okay. A lot of students complain at this point and say, whoa, what about, look, there's clearly some values of y over here. Why don't we think about those values of y for, a point like this? Seems like a reasonable complaint, right? You got to keep in mind what we're interested in how the y bounds depend on x. The overall y bounds don't matter. We want to know how do the y bounds depend on x. And so for the green value of x, in other words, for this overall x slice we're interested in, we don't get to this point at all. It's part of our solid. How can we get away with ignoring it? We're not ignoring it. We will get to these points for different values of x. Right? So don't worry about it. We'll get there. We want to know how the bounds depend on x. Is everybody happy with that? That's a subtlety that messes up a lot of students. A lot of students will look at this question and say, well, look, x clearly goes from 0 to 1, and y clearly goes from 0 to 1, and z clearly goes from 0 to 1. And they'll say 0 to 1, 0 to 1, 0 to 1 here. And that's first of all, that would be a rectangular box, which is not what we have. But the point is, it's misunderstanding the process and what we're interested in. Everybody happy? Okay, so again, let's play the first and last game. So the first value, the lowest value of y is going to be on that slice that's in the plane y equals 0. So y is 0. And again, sometimes you get freebies, capitalize on the freebies. The last value of y comes from that point. Here's where we have to do our job again. Here's where you have to actually think through the process. That point, let's see here. Well, it is, according to the picture, it's in that face. That face has that equation, z equals 0. Thank you, picture. Let's see, what else can I say about that blue point? Well, it would appear, again, from the picture, that it's in that face. Which, again, the equation was given. Write that down too. And the third thing that we know about that point, this is easy to forget, very easy to forget, but don't forget we've fixed a value of x, right? We have x given, or said differently, we are focused on looking at this green slice. Now that green slice represents an arbitrary value of x. It's not where x equals 0. It's not where x equals 1. It's going to eventually be all the values between 0 and 1. But it's x is what it is on that slice. And my little hacky, but I find satisfying way to write down that x is what it is to write x equals x. I don't know, I find that satisfying. You don't have to do that. But just keep in mind, the point is x is a given, and so your answer is allowed to be in terms of x. In fact, you should expect that the inner bounds will be functions of the outer variables. Okay, so again, easy to lose track. What are we doing here? There's points, there's slices, there's faces. Oh my gosh. Don't forget, we are looking for a bound on y. So the whole point to all of this algebra is that we want to solve for y. And when you do that, you get 1 minus x for our upper bound. Questions? Everybody good? Everybody happy? Again, don't think about the algebra. The point to this is not that the algebra is easy. The point to this is that we're following a process to get the bounds by, again, following certain rules and procedures. Okie dokie. Just like on the previous page, now we're going to say, hey, not only is x fixed, but also y is going to be fixed. We're fixing both of these. We're therefore imagining some point, you might say down in the shadow, down in the xy plane that represents our chosen arbitrary values of x and y. Excuse me. And then for that value of x and y, those values of x and y, we want to look and see how z varies. We want to find our range of values for z. Z starts here, where I'm going to say z is obviously 0. again, kind of thank you picture again, right? It's the picture is what makes that clear. And then Z is going to end here. And again, we got to think it through. What do we know about that point? This point that represents our upper bound for Z. Well, that point is on that face, again from the picture, that equation. Again, don't forget, we already know X. We already know Y. Or said differently, we want to know how Z is a function of X and Y. So those are given. And so you want to find this upper bound for Z. We solve for Z. And there it is. How are we doing? Is everybody with me? Is everybody happy? Okay. That's the process. Now, we're going to do a bazillion more examples. Pretty much this is the process. Now, there's a different take on this, and I have a sort of a favorite streamlined shortcut, you might say, version of this. It doesn't always work, but very often it does. And in cases where it does, the shortcut is very handy, and I'm a big fan of the shortcut, and I encourage you to use the shortcut that I'll show you next. But let's not lose sight of the fact that the shortcut is just shortcutting this process, and this is basically how this should be your default cornerstone point of view on how to turn triple integrals into iterated integrals. Is think about the slicing, think about each relevant point, what do you know, what surfaces, what equations, etc. Okay, a couple of bits of advice. I think these are no surprise, stolen from our observations about double integrals. Try not to slice through corners. Bad things happen when you slice through corners, right? We saw an explicit example with a double integral. You slice through a corner, you're going to have a whole new iterated integral to deal with. Nobody wants that. It's even worse for triple integrals, by the way. So extra be sure not to slice through corners. And then also think strategically about what variables would you like to solve for. You're going to have to solve for something as a function of the others. Choose wisely, and whatever variable you would find most convenient to solve for, put that one on the inside, because that's where you're going to have to solve for it, right? So don't paint yourself into a weird algebraic corner unnecessarily. Okay. This last little bit of advice is going to make more sense after we've seen an example where we're going to actually use this. So I'm going to momentarily skip this, but we're going to go on to this next example, and I'm just going to talk through and explain a convenient sort of way to shortcut the process, and the punchline in the general lesson is going to be this. So we'll come back to that. Here's the example. Now y'all got to think through the geometry on this one. But so we're going to look at that plane, z equals 1, that paraboloid. Make sure to remember all that chapter 2 stuff with surfaces, right? And there's a certain region that's bounded by those. In particular, there's a certain region that is the first octant portion of what's bounded by those. So that's our solid, and here's my drawing of the solid. Make sure you can think that through, and then while I'm at it, let me make a pitch for how important it is to be able to make decent drawings. Right? So you saw how much we relied on the drawing for the arguments that we made here. Right? Upper bounds for which variable depend on which points. Those points are on which surfaces, and it's the picture that tells us. Right? So it's basically essential to have a decent picture, and you're the one that's going to be producing your pictures, right? So it's very valuable to be able to make decent pictures. You don't have to be able to make beautiful pictures, right? But they need to be at least good enough to be interpretable. So I'll remind you all, everything I know about mathematical drawing, I put in some videos that are on my miscellaneous topics playlist called Drawing 1 and Drawing 2. Not very creative naming, but pretty clear. The first one is the tips and tricks. The second one is some explicit examples. And this very drawing is one of the ones that I go through in gory detail, right? If you want to know exactly what was I thinking when I drew this line that way instead of that way, I mean, all the little subtleties of every little aspect of this drawing discussed in great detail in that second recording. So I hope you'll take a look at that. And we, again, are going to rely heavily on the picture here. Okay, so here we go. First thing doesn't need the picture at all, but I see this, and I immediately have an opinion about something. Would I rather solve for X, Y, or Z? Again, strongly felt opinion. I'd much rather solve for Z. Not only has it been done, it's the only one that wouldn't require square roots. I don't like square roots, right? I don't think you probably do either. So, cool. Let's figure out how we can capitalize on that. And the way we're going to capitalize is to choose to put Z on the inside. And therefore, process of elimination, X and Y on the outside. Which order you do these, in this case, kind of doesn't matter. Some cases it does. Every example is different. In this case, it doesn't matter. Everybody good? Everybody happy with that? Okay. Alrighty. So that in mind, let's start our slicing. Let's see. We'll start apparently with the Y slicing. There's the Y-axis, Y slice, perpendicular to that axis. Going to look something kind of vaguely like this. A little bit hard to draw. By the way, I critique my own drawing here in a couple of different ways. But anyway, that's going to have to do. That's the best I can do in a reasonable amount of time, and it'll be good enough for our. Okay, so the first such slice will be way back here, and then again a generic slice is like that, and then the last slice is there. Now, quick side note. Now, I could play the usual game and look at these slices and think about what I know and solve blah blah blah. I'm going to do something a little different here. Notice, if I were to think about the shadow down here, the shadow in the XY plane, if I were to slice up the shadow instead of the solid, well, here's the first slice, here's a generic slice, and here's the last slice. And notice, they correspond. Right, the range of values of Y on the solid is exactly the same as the range of values of Y on the shadow of the solid. Everybody see that? It's one of my big insights here. Okay. Cool. Okay, let's look at generic slice then. And let's think about next, we're going to go in the X direction. So as I go this way, well, my X slices, there's the first one and there's the last one on the solid. By the way, let's do the same thing for the shadow, right? On this slice of the shadow that we have, there's the first one and there's the last one. And again, notice they are right on top of each other. The range of values of X on the Y slice of my solid is exactly the same as the range of values of X on the shadow of the solid. So here's the takeaway then, and by the way, this always works. Correction. Once you've identified what are going to be your outside two differentials, in this case X and Y, when I say shadow, I mean shadow toward that plane. So here we're looking at the shadow, which is the projection into the XY plane because X and Y are the outside two differentials. When you make that choice, when you look at that shadow and compare to the solid, the range of values of those outside variables will be identical on the solid and the shadow. Is that cool? Everybody buy it? Okay, so I'm going to call this a big win because the solid is hard to draw. The slices are hard to draw. By the way, y'all are getting the benefit, the advantage of I've already done the drawing, right? But it's hard to draw. I'll give it a try. And can be more confusing, can lead to making mistakes because it's hard to visualize. The shadow it's a quarter disc. It's super easy to draw. There's no particularly challenging effort in slicing up that shadow. So the process that I encourage in situations where this makes sense is you look at the shadow in the plane defined by the outside two differentials, and then you slice up that shadow to get your outside two lower and upper bounds. You everybody see the play there? Does that make sense to everybody? Okay, all right, so I'm going to call that a nice streamlining. Now there is a further streamlining. Keep in mind, we're now with X and Y bounds chosen, we're going to fix X and Y. That means we're basically going to fix a point in the shadow. And then above that point in the shadow, we're going to ask, what's the lower bound for Z? Well, it's going to come from that point. And what's the upper bound for Z? Well, it's going to come from that point. And let's play with these one at a time. Very conveniently, let's just keep it streamlined. Very conveniently, this lower bound, wrong color. This lower bound point, that point that that is the lowest value of Z on this X slice of that Y slice, is always on that surface. It's always the same surface. Consistently. No matter what values of X and Y, no matter where you are in this shadow, your lower bound is always on the same surface. That's handy. Very convenient. And it gives rise to, you play the usual game, and it's going to give rise to that lower bound for Z. And then likewise, the upper bound, always going to come from that point, and check it out, picture appeal, that upper bound point will always come from, again, the same surface. No matter where you are in the shadow, the upper bound point is always on that surface. Solving for Z will then give you the upper bound. Everybody see that? Okay. All right. So let's talk about the takeaways here. This list of this kind of summary of this process is just noticing what worked so well. We focused a lot on the shadow, so it's good that shadow was something that's easy to play with, right? It wasn't it was just a quarter disc. It's no problem, right? So the fact that was an easy shape to deal with, good thing. And then recall the top and bottom surfaces, right? Those top and bottom surfaces were always the same, right? The top surface is always the same surface, no matter the X and Y. Consistently, you might say, the same surface. And again, algebraically easy to deal with. Okay. And so with those established, you just look at the projection. The projection gives the outside two bounds, and then the top and bottom surfaces give the inside bounds. Simple as that. It's a really nice process. Now, again, conditions, right? You got to make sure that shadow is nice looking. You got to make sure, this is not always true, got to make sure the top and bottom surfaces are consistent and desirable. Otherwise, this doesn't work. Right? But surprisingly often, all these conditions are met, and you can totally use this method. Let's see another example. Let's see if I can squeeze. There we go. Okay, so we're going to use the unit ball. Do a triple integral over the unit ball, and you can play the usual game. The usual game you would think would be pretty easy. It's just a ball. Something kids play with. How hard can it be, right? It turns out it's actually kind of annoying. The art that's involved is harder than it looks. It's easy to draw a ball, but then when you say I want to look at a particular value of x and draw a cross-section of that ball, well, we know that's going to be a disk, and I went to some trouble to make this actually look kind of reasonable, but it already kind of doesn't look quite right. I feel like this, shouldn't it be weirder than that? Along in here, I'm not sure this is quite right. And then notice when you turn your attention to that slice, and you want to think about as you now go in the y direction, and as you go in the y direction, your values are sort of like this that you're looking at, and this gets a little tough to imagine geometrically and worse to draw. So it can be confusing, and you can do it that way, and fine, go ahead, and maybe that'd be a good practice problem, something to think through. Let me show you what I think is the much easier way to do it. Arbitrarily here, I've put x and z on the outside. Let's play the projection game. All right. Well, in the xz plane, our projection is a disk. Furthermore, it's clearly the unit disk. Super easy to redraw. I'm going to do that just because it's easy, and why not? Hang on. There's our unit disk in the XZ plane. Y'all know how to slice up two-dimensional regions. That's not hard to draw. The algebra's not that bad. Well, there's a square root. What are you going to do? There's no way to avoid that we know yet. Foreshadowing. There's a better method that we'll talk about later. But for the moment, no big deal. And this is a good exercise. Make sure you can do this. Looking just in the XZ shadow, there's the X and Z bounds. Two-dimensional picture, and I don't have to think about slices of slices and which way, and oh my gosh, the hard to draw. No, just it clearly has a projection that's a disk, and disks slice up like that. Isn't that nice? It seems a little too good to be true. And then the last thing you got to do is say, well, I do have to think about the y bounds now. Well, so y for a given value of x and z, let's look, I don't know, let's say about right there. Y is going to range from somewhere over here. Oh, let's see, let me think carefully about somewhere over there to somewhere over here. By the way, I don't want to muddle my picture, so I'm going to get rid of all this stuff here. Again, we have this fixed values of x and z there. And, well, check this out. This lower bound point, the lowest value of y, quick little geometric appeal, it's always going to be on what you might call the Western Hemisphere. In easy algebra, x squared plus y squared plus z squared is 1. Y has to be negative because that's what the Western Hemisphere is. And then let's see the upper, and then, oh, by the way, solve for y. And there's the corresponding y. Then the upper value of y will come from this point, and that point is always on what you might call the Eastern Hemisphere. Again, same equation, x squared plus y squared plus z squared is 1, except now y has to be positive. And so that upper bound, solving for y, is that. And my own feeling, everybody's different, and that's fine. My own feeling is that this was artistically and geometrically so much easier than playing that slicing game. So I think the projection approach here, super handy. Everybody happy? Okay. Alrighty. Next example. This is a really cool example in multiple ways. I'll talk about what's cool about it later. It's a little bit of a scary example because I give you 5 planes and then I ask you to understand the region that is bounded by these 5 planes. Now let's just take a quick moment. If I were to give you 5 random planes and ask you what region does that enclose? Oh my God, I don't even, nightmares. I could probably come up with something, but wow, that'd be really hard. Really, really hard. That would be an unfair problem. I wouldn't do that to you, right? That's not reasonable. This is not 5 random planes, right? These are 5 suspiciously convenient looking planes, right? And that's going to matter a lot. So the big foot in the door in this case is you will notice 3 of these planes have a certain feature. Again, it doesn't quite leap off the page at you, but once you see it, it's hard to not notice. 3 of these 5 planes don't have any y's in the equation. And I hope y'all might remember back in chapter 1, like way long time ago, this was one of my little extra observations that I pointed out. Neat, easy fact. Easy to notice, powerful conclusion. If there's no y's in the equation, it's parallel to the y-axis. So we're going to use that fact. Now, knowing that these are parallel to the y-axis, it's actually pretty easy to, I'm going to need to distinguish that color. It's pretty easy to draw the planes because all I really have to do is draw what they look like in the XZ plane. And that's good enough because knowing that they're all parallel to the y-axis, I can just kind of drag. Oh gosh, excuse me. I can just kind of drag parallel to the y-axis, pretend that those are parallel to the y-axis. And I get this kind of prism-looking shape that you can see that we've got there. Does that make sense to everybody? Golly, I'm sorry. I've got some allergies. It's just allergies. Okay, so so that makes the drawing a lot easier. We're 3 out of 5 down, and what's left are not that bad. So, in particular, y equals 0. Oh, that's easy. There's y equals 0. How does y equals 0 cut through our prism? Well, that's also pretty easy, and it just cuts this face here to the left. That makes sense. And now we got to look at the remaining plane, and this one is legitimately a little harder. Sometimes life isn't convenient. That plane is something like that, and just annoying to have to do this, but you got to think with your geometric intuition. We've got this prism kind of going this way parallel to the y-axis. This plane is kind of cutting through. It's not, like this parallel to the x-axis, and it's not. It's at an angle. It's sort of angled in all 3 directions, if you will. And if you think about how that cuts through geometric appeal, it's going to give you something kind of like this. Whoops. Something kind of like that. I always feel the need to get that. There we go. And for the details, how do you know where this point is, for example? Well, that particular point, how where that corner is, you can notice that that's on this face, and it's also on this face, and it's also on that face, and then you can solve that little trio of equations and find the coordinates at that point. And then you can likewise do that for any other points that maybe you're not entirely clear where they are. How we doing? Everybody happy? So note a pretty significant little challenge there in just figuring out even, from the statement of the question, what is this domain? What does this thing look like? Right? Non-trivial, what this looks like. Okay. So I wanted to make sure y'all saw that little trick. And now let's start thinking about the slicing. And now if you want to, do this the old-fashioned way and slice and then slice the slices and, that usual game, well, there's 6 different options to try. And what you're going to find is that 5 of them slice through corners, which, of course, we try to avoid if at all possible. By the way, side note, sometimes it's not possible. Sometimes you have to slice through a corner. And Kali has a nice homework exercise that is on the content syllabus that y'all will be doing, where there's no way to avoid slicing through a corner. And so sometimes you just have to deal with a couple of separate iterated integrals. So, sometimes that happens. But in this case, look at this solid. There is an order to go in which you hit no corners at all. And it's this choice right here. I think it would be a lovely exercise, and I want to encourage everybody to do this, to try the other 5, see how those slices hit corners. So, for example, if you put dx on the outside, and your very first slices that you do, in other words, are perpendicular to the x-axis, well, your slices are going to look like that, and then check it out. You will eventually be slicing through that corner. Everybody see what I mean? So think about the others, right? So all 5, not including that one, will slice through a corner one way or another. And again, just no good. You don't want to do that. But this one's okay. And so another thing you can do, and I encourage this, is go through the slicing process. Draw the slices and think about the slices of the slices, etc., with this ordering of the differentials. And it works fine and dandy. But then look how great it is if you just kind of skip that whole thing and just think about projections, right? If we pick, the xz projection, and notice I put the dx and the dz on the outside so that I can have the xz projection to look at. From that point of view, and then looking at the range of values of y, notice we always start on this plane on which it is easy to solve for y. And we will always end on this plane on which it is easy to solve for y. And it's just a lot easier to get to your iterated integral by thinking about that projection point of view. Is that satisfying for everybody? Okay. So last thing I'll say about this example, there are a lot of students in this class who have taken high school multivariable calculus classes, and in those high school multivariable calculus classes, little partial truths are told sometimes, such as, you can just look at the equations from what's given and notice that what the equations are going to tell you what some of the bounds are going to be. and that this is somehow a reasonable way to find your bounds. So 2 reasons why that's not a reasonable way to find bounds. One is it's not an analytical argument. It's equivalent to saying, well, you gave me this and I didn't know what else to do with it, so I guess I'll stick it here. It's just not an argument, right? The other thing is, it does not work. It regularly doesn't work, and you don't even have to go to that much trouble to find an example. This, I think, is a really nice one. I challenge anyone here to look at the statement of that question and to so much as even realize from just the statement of the question, without drawing the picture, what is it about the algebra here that makes it perfectly obvious that dy dx dz is the only way to go? And I say, no, it's just straight up not clear. I'm not saying that there isn't an argument that can be made. I'm saying it's not immediately clear. It's not even kind of clear. Right? Does everybody see that? Right, so this idea that, oh yeah, you just look at the algebra and write down the bounds, nonsense. Doesn't work. It's not an argument, and you cannot count on it. It will not work in many situations, this being one of them. So, okay, I hope that's helpful. We'll draw the line right here. See y'all later. Have a good rest of your Wednesday. See you Friday.